Okay, so last time we talked about the valence shell electron pair repulsion theory. We call it VSEPR. And we said that this theory basically has 5 shapes or 5 molecular geometry or 5 arrangement of electron atoms. There's the linear, trigonal, planar, and there is tetrahedral. There is other two, by the way, trigonal, pyramidal, and octahedral, but we're not going to study these two. So basically, we have three main families or arrangement of electron pairs, which is the linear, and linear has only one shape or has one molecular geometry, which is the linear. There's also trigonal planar, which looks like a shape with a fan with 120 degrees, and this one, the trigonal planar, has two sub shapes, the trigonal planar itself and the bent. We have also tetrahedral, which has 3 subcategories: the tetrahedral itself, the trigonal pyramidal, like ammonia, and the bent structure. So these are the arrangement of electron pairs and molecular geometries that you need to pay attention to and to determine the shapes. And from that, you can also determine the physical and chemical properties of some molecules. And we have some examples like water and ammonia and some other stuff. Let us continue with this today, and we'll dig more into some more shapes and see how they look like. Last time in this example, we also solved the first two, the A and B, and I think also I solved ALCl4 for you, and we found it to be tetrahedral. Let's continue this today. Let's start with a nice molecule, which is sulfur dioxide. So sulfur dioxide, we're talking about sulfur dioxide gas, so it's a molecule, it's not an ion. If we need to draw the VSEPR structure first of all, of course, we need to start with Lewis. And the first step is to count how many electrons that we have. Both sulfur and oxygen, they are in the group 6, so they have 6 electrons in each. And that will give you 18 electrons. Let's put sulfur in the middle first. Have at least one bond for oxygen, at least one bond for oxygen. Of course, these are not enough electrons here because you have 18 electrons, so you need to finish this up. So maybe try to do this first. That's 8 and 8, 16. There's still 2 electrons left. We're gonna put them in sulfur. You will find here that this is not good because even this will achieve the octet. This one will achieve the octet. The sulfur is not achieving the octet. It has 6 electrons only. So a better way to do it maybe to bring these electrons in here, and that's not the only thing that is wrong with the structure. Is that also the formal charges? In terms of formal charges, you can practice this yourself, and you will find this to have -1. This is -1, and how much is sulfur? Sulfur is 6 minus. It should be +2. Yeah, 2, 4. Yeah, exactly, +2, because 6 minus 4 is +2. So that's a low structure, but it's not acceptable. There is way better one by moving these 2 lone pairs in the middle and making double bonds. That will give you, of course, this one with only 2 lone pairs here, 2 lone pairs here, and 1 lone pair. So this one is really good. 2, 4, 6. They have all 0 formal charges, 0, 0, 0, and they all achieve the octet. The only thing, this one has 2, 4, 6, 8, 10. This one is expanded octet. Okay, expanded octet for sulfur, because in this case sulfur in the middle has 10 electrons, but that's okay for sulfur. It can exceed the octet as we said last time. So this is the lowest structure. Okay, now let's think, what is the VSEPR? And the VSEPR is actually the one that is the VSEPR is actually the one that is the real structure, right? It's lowest. It's not the real. It's not the real structure. It's the VSEPR that is more realistic. Now we have this situation here where sulfur in the middle. We have 1 O and then 1 O and a lone pair. Now let's count the arrangement of electron pairs around the central atom, which is sulfur. This is equal to how many? You have now for the VSEPR, you count the double bond as 1. Okay, you count the other double bond as 1 and the lone pair as 1. So this is what I said last time. So this is 3. So in VSEPR, single bond, double bonds, lone pairs, they all count as 1. Even a triple bond count as 1. So this is what the VSEPR theory here. So the arrangement of electron pairs around the sulfur atom and SO2 is a 3, and this one will give you will give you a trigonal planar. That's the arrangement. That's the big family. Okay, trigonal planar. And because of that, then you're expecting around 120 angle. Okay, so this is O here, O there, and this angle is around 120, and this angle is 120, and this angle is 120. Because lone pair needs more space, okay, and this angle here should be, because the lone pair needs more space, maybe the lone pair will push these bonds a little bit further, and this angle will be actually a little bit less than 120. So let me show you this in fit.com. How does it look like so you understand better? In fit.com we start with this. So we have a sulfur in the middle, and we have oxygen. So we need to replace this with double bonds. So we need to remove that. Now this is it for sulfur and oxygen. So it looks linear, but once you put the lone pair, that's not good. You have to choose the other one, not the basics. The molecular shape, the black one. So you can always use this in fit.com to help you understand that. So we need 2 double bonds and no single bonds. So this is it, and I need to add 1 lone pair, and this is it. You see that it's a trigonal planar. If you click on the molecular geometry, fit.com call it molecular. Okay, the electronic geometry arrangement of electron pairs in fit.com. He calls it electronic geometry, and that's trigonal planar. Trigonal planar means this belongs to the AB2E, okay, or just like BH3, just like boron trihydride. It is a trigonal planar molecule with 1 lone pair sitting 120 degrees from the oxygen atoms. Okay, so this angle is at 120 degrees. Okay, you can actually go to real molecules. Go back and start this again. Choose real molecules. I think SO2 should be one of them. Probably SO2 is right here. You see, he is drawing SO2 for you with a trigonal planar geometry, and the shape is bent. Okay, the shape is bent. So recall that water was bent as well, but water is a different story because water has 2 lone pairs on it. Okay, so here it is. This is bent, and this is bent, but these ones, they belong to different families because this one is a trigonal planar, and this one is tetrahedral. Now what do I mean? What do I mean by bent and trigonal planar and all this? This is the family. The trigonal planar is the electronic geometry. Okay, this is the arrangement of electron pairs. The trigonal planar is the arrangement of electron pairs. This tetrahedral is the arrangement of electron pairs. That's a big family. These molecules belong to. Bent is the shape of the molecule. Is the actual shape of the molecule. Okay, so they are both bent, but they belong to different arrangement or different electronic geometry because of the fact that the water has 2 lone pairs and sulfur has 1 lone pair. Going back to fit.com, you can switch this to water. You see, water is also bent structure, okay, and you can read here at the bottom left it says bent, but the electronic geometry is tetrahedral. Okay, I3 minus is not with you guys. I3 minus is one that is the group that is cancelled. It's called trigonal pyramidal. But let me just show you what does that mean anyway. It's not at this level of chemistry 101. I3 minus is not required from you, but let's do it anyway for the sake of lowest structure at least. So I3 minus iron is in group 7, so you have 7 times 3 plus 1, and that plus 1 is for the negative charge, and that will give you 22 electrons. So of course I3 minus, there is no way but just to put them all in one line. Now you have 22 electrons, and now you have here only 4 electrons, so you need to complete the rest of the electrons. So that's 8 and 8, 16. This is 8 electrons, okay, and this is 8 electrons, 16. There's a lot more to finish. You have a lot of lone pairs on the iodine, okay. If you want to draw it with the conventional way, you have to put circles here, okay. That's why I put dashes, just to be quick. But in fact, this is the I3 minus lowest structure, okay. And if you want to count the octatrol and formal charges, octatrol for this I to the left, it has 2, 4, 6, 8. It achieves the octatrol. This one is 8. This one in the middle has 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. It has 10 electrons. So this is expanded. Ask you which one of these molecules has an expanded octet. This one is an example of a molecule that is exceeding the octatrol, and that's fine. Iodine is sitting down at the periodic table. It has d orbitals. It's empty. It can be fine. In terms of the formal charge, iodine is in the 7th group, and if you cannot count this 7 minus how many electrons? 2, 4, 6, 7. So this one is actually 0, and this one is 0. This one here in the middle, it's in the 7th group minus how many electrons are around this at the moment? There are 2, 4, 6, 7, and 8. This is how I count for formal charge. I explained this before. So this is minus 1, and it makes sense because this one is, the whole thing is minus 1, okay. So the final structure would look like something like this. This is the final structure, okay. You have to put the minus 1 here, as I said. Okay, this is the final lowest structure for I3 minus. And if you want to think about VSEPR, the arrangement of electron pairs around the central atom is equal how many guess? Any guesses? Anybody? 1, 2, 3, 4, 5. You have to count the single atom as a single bond as 1, and there is 2. One lone pair counts as 1, so 3, 4, 5. It has 5, and this is something we didn't study before. This is called trigonal pi pyramidal, okay? 5. And here in fit.com I can show it to you. So you take a model and you can start all over again. So you click a model and okay, so you have to go back for you to previous step, not to a real molecule but to a model. This is a model. So for I3 minus, you want to put, this is a good start, single bond, single bond. Now, how many lone pairs you want to add? You want to add 3, just like, this is the structure of I3 minus. So it's linear. The shape is linear. Okay. So indeed, the shape is linear. Because it's sitting in a straight line, this is a 180-degree angle. Okay. But it's not the linear group that we studied. This is different group here because you have a lot of lone pairs on the middle. And if you click on the electronic geometry, this is called trigonal pi pyramidal. It's not required from you guys, but just to show you, this is trigonal pi pyramidal, and the molecular geometry is linear. Okay, it's beautiful. There is one more actually. It's called octahedral. It looks like this. 1, 2, 3, 4, 5, 6. Okay, so the 6 group. This is called octahedral. Okay, octahedral, and you can play with this, removing one bond and adding. This is also part of octahedral and so on. Type. And that's it for now for the VSEPR structure. You can do, of course, some more later on. But does anybody has a question? Anybody needs? Okay. Let's talk about dipole moment. I think we studied before the concept of polarity, that some molecules are polar and some of them are not. And this is because of the shift of the electron density. So in polar covalent compounds, there is a shift of electron density from the less electronegative element to the more electronegative element. And I think we described HF before, hydrogen fluoride, where the electronic cloud is more concentrated on the fluorine atom because of the fact that the fluorine atom is much more electronegative than hydrogen. And this is where we use these partial charges, partial negative, delta minus, delta plus. Delta minus means you have more electrons on the fluorine rather than H. So this molecule is indeed a polar molecule because all the electrons are towards the F. Now we have some, so this is a polar bond. Now a polar bond does not indeed mean that the whole molecule is polar. You have we will have examples of a molecule that have polar bonds, but the whole molecule is non-polar. And this is where we define the dipole moment mu, which is the measure of the net molecular polarity, okay? Measured as the magnitude of the charge Q at the end of molecular dipole moment multiplied by the distance R between the charges. So HF is, so for mu, which is called the dipole moment, okay? It has a value for HF, and it doesn't matter at this point how do we calculate this value. But the more important thing is that here mu is not equal to 0 because this molecule is polar and the dipole moment is towards the fluorine atom. If you put HF in a magnetic field, okay, there is no need for these molecules to be attracted because there is nothing attracting them. You will have the two ends of the HF, the plus and minus, arranged in different ways. But once you put this once you turn the magnetic field on, okay, the positive pole of the magnetic field will pull the negative fluorine, and the negative pole will attract the hydrogens, and you will find these HF to be arranged, okay, nicely within this is the fold. This is how we determine experimentally if the molecule is polar or not. Now, let's talk about CO2 and find if it is polar or not. Now, for CO2, we have not drawn the VSEPR structure of CO2 before. Sorry. So CO2, for carbon has 4 plus 6 times 2 for the oxygen, 12, 16, okay? So you can start with this, of course, with a single bonds. You will find that this is not good. This is the 16 electrons. This is not acceptable lowest structure at all because carbon is in the one of the atoms that has no tolerance with the octet rule. So you must do double bonds, okay? And you will find this structure to be more reasonable, okay? Where everybody is achieving the octet rule and everything. Okay, so this is lowest structure. Now the arrangement, this is lowest, okay? Lowest is not always equal to VSEPR. Now what about VSEPR? The VSEPR, we need to talk about the arrangement of electron atoms on the central atom. So arrangement of electron pairs You can call it also electronic geometry. Electronic geometry. This is equal to how many? 2, okay? Because you count double bond as 1, and you count the double bond as 1. So 2 means linear. So this is a linear group, a linear shape, okay? Linear, linear. This is how I do it. What does linear mean? Linear means the arrangement of electron pairs is linear, and the shape is linear. Okay? And going back again to fit.com, you can simply do that by doing this 1, 2, okay? And taking out the single bonds. Sorry, taking out the single bonds. Just add. So what is this? Linear molecule. You click in the molecular electronic geometry, it says linear, and the molecular geometry is also linear. So they are both linear for CO2. You can also go back and choose a real molecule. CO2 is there. It will show you that here, real molecule. See that at the bottom it says real molecules. Click CO2. This is CO2, linear, linear. Now let's think about this molecule, if it's polar or not. Now many of you will say it is non-polar, and they know why. Well, CO2 is CO2 polar. Well, let's think about it. C in the middle, O, O. Now, which one is more electronegative? Oxygen is more electronegative than carbon, so it's going to attract the electrons this way, and the other oxygen will attract the electrons this way. But the attraction will be in the same direction, sorry, in the same amount, but different directions. So the net dipole moment is equal to 0. Anybody studied physics, she knows that if you pull towards the right and left, the net force on the carbon will be 0. Just imagine this is a horse pulling a ball to the right, and another horse pulling to the left, and they are equal horses in the same ball. The net force on the central atom will be 0. In chemistry terms, the net dipole moment is equal to 0, and this mu is equal 0. So this is non-polar molecule. Non-polar molecule. Determining the polarity of a molecule is very important in chemistry to determine chemical and physical properties. So in CO2, this bond is polar bond, okay? But the whole molecule is not polar. Okay? In HF or HCl, Cl is way more electronegative than hydrogen, so the electrons are pulled that way. Okay? So the dipole moment indeed is not equal to 0, and therefore this is a polar molecule. So this is a polar bond, and the whole molecule is polar. Now the question is, yeah, yes, go ahead. Yeah, go ahead. I'm listening. Well, it depends. It depends. In CO2, when we draw the CO2, you draw one line here. You see that when you are drawing one line or a single bond, you count how many electrons around carbon. You have 2 and 4. So you only have 4 electrons around carbon. This is not good. Carbon does not. This molecule violates the octet rule, and it's not acceptable. So you must. Yeah, unless you have other situations. You have to solve. You might need to add double bonds to other elements. You need to solve so many examples, and you will practice this, and then you know where to add the bonds. It comes with practice, yeah. Type. CH4, let's think about it if it's polar or not. So here is CH, H, and H, and H. Now these are polar bonds, by the way. This is a polar bond. The bond itself is polar because the bond is towards the carbon, okay? But these all bonds, they will cancel each other. If you think about CH4 and as a real molecule. Methane, this is methane. It's a beautiful molecule. All the bonds are directing at exactly 199 degrees from each other's, and these all, they cancel each other's, okay? So if you think about it this way, and the upper two hydrogens will have a net dipole moment to the top. The lower hydrogens will have a net dipole moment to the bottom, and they will cancel each other. So methane is indeed non-polar molecule. Okay, so this one is a non-polar molecule. But if you change any of the hydrogens to anything else, let's say you are studying CH3Cl, which is a chloroform. Sorry, it's a chloromethane, it's not chloroform. So this is chlorine, and this is hydrogen. Now the story is different, because now here you have unequal pulling. You have here that the carbon is pulling this way, the carbon is pulling this way, but chlorine is more electronegative than the carbon, so the pulling will be that way. So you have a net dipole moment that is going up, and therefore mu is not equal to 0. It does have a value 1.2, 1 point something, and therefore this one is indeed a polar molecule. So as a homework, please, for everyone, and please bring the answer on Saturday, on Thursday. Is this molecule? This is called dichloromethane. Okay. I always give this to my students as a homework. Is this polar? Think about it, and don't answer now. Okay. Just tell me next time if this is for dichloromethane. Okay. Type. So this is all explained here. Of course, ammonia is polar because you have a net dipole moment that is not equal to 0, as cleared here. And this is another two examples of a molecule called dichloroethene. Now, can dipole moment be used to distinguish between molecules that have the same formula but different structures? The answer is yes. Take this example. This is dichloroethene, I mean, or dichloroethylene, and this is the cis and trans isomers. Okay, the cis is where the two chlorines are in the same direction, and the chlorines are in opposite directions. For the cis, you see here that there is a dipole moment that is actually going up because the chlorine will shift this way. Chlorine is more electronegative than carbon, so it's going to shift the electrons this way, and this one will shift that chlorine this way. Okay, and therefore you have a dipole moment, and net dipole moment is up. So the net force on the double bond is not equal to 0, and this for the cis, we accept this is to be polar. This is indeed polar. But for the trans, you see that the chlorine will pull the electrons to the right this way, and this chlorine will put it to the left. Carbon will pull the hydrogens this way, and the other carbon. So everything cancels out here. This is a symmetrical molecule. It's a very beautiful molecule. Okay, all molecules are beautiful, but this one will be non-polar. This one will be non-polar. So it's the same compound, but it's different orientation, different structures, and therefore the cis is polar, and mu is equal 1.89 D, and D, if you remember from the definition, is called D-bind. Okay, so you have to measure the dipole moment. You don't have to actually calculate or measure the dipole moment. This is advanced stuff, but at least you just need to know that the dipole moment in the cis is equal a number. It's equal 1.8, so it has a value, and therefore this is a polar. And for the trans, this is a non-polar molecule with mu is equal to 0. Now, predict whether each of the following molecules has a dipole moment: A, BrCl, B, BF3, and C, CH2Cl2. I assigned CH2Cl2 as a homework, but let me do A and B. So A will be polar, of course, because BrCl, it's just like HCl. This is easy example. So BRCl, you have only this. It's 7 plus 7, 14, okay? That means 2, 4, 6. How much is this? 8, yeah, 14 electrons. That's good. Now, which one is more electric? It doesn't matter here which one is more electric. They are different elements, okay? They are different elements. Either this one is more electronegative or this one is more electronegative. You will have a net dipole moment that is going somewhere. So mu clearly here is not equal to 0, and this is of course polar molecule. If you have the same elements, you have, let's say, Br, which is Br2. Of course, this is going to be non-polar, where mu is equal to 0. That's an easy example. Let's talk about BRF3. BRF3 is just like, okay, this is not, this is BR, it's boron, BF3. We did this before, boron trifluoride. Maybe we did it before BH3, the same as BH3. Okay, so boron is in the third group. That means you have 3 electrons plus 7 times the 3. This is just like so 21, 24 electrons. So to answer, now the girl is asking double bonds or single bond. You pay attention here, please. This is the lowest structure. You start with single bonds and you think, is it enough or not? Now this is lowest structure for single bonds. Now you have 24 electrons. Where are you going to put them? Let's put them here for fluorine first to achieve the octatonal for fluorine. Okay. Now if you think about this, 8 times 3 is 24. So there are no electrons actually on boron. No electrons, no lone pairs. Single bonds, well, this is 8. This is 8. This is 8. This is 6. It violates the octet rule. That's fine because boron does violate the octet rule. You cannot do double bonds here. If you want to do double bonds, then you will find that fluorine has some formal charges and it's an exceed the octet rule, and fluorine cannot actually break the octet rule. Okay, so that's fine so far, and fluorine usually does single bonds anyway. This is the lowest structure. And please don't make the mistake by predicting polarity on lowest structure. Okay, I'm going to write this down here for you. Never predict polarity based on lowest structure. That's very big mistake. You need to draw the VSEPR, and you can do that from the VSEPR. So boron trifluoride, of course, according to the VSEPR theory, there is no need for these fluorines to be at 90 degrees. This is 120 degrees because the boron trifluoride is trigonal planar. Okay. Trigonal planar, that means you have 120 degrees, and you see it's a beautiful molecule. If the fluorine is pulling this way, this one is pulling this way, the net force on this is 0, and therefore this is a non-polar molecule. But if you change again any of the fluorine to anything else, let's say you have a molecule that says BF2Cl, okay? BF2Cl will look like that. Okay, that's a different story now, because the fluorine is pulling this way, this chlorine this way, but you have unequal pulling here. Unequal, something will cause the mu not to be equal to 0, and therefore this is a polar molecule. Okay, so that's the difference. This is non-polar for BF3, but BF2Cl is polar. I just want to go back again to my note about don't predict polarity from lowest structures. Just imagine water. Water, according to Lewis, is this. is a linear structure actually. This is water according to Lewis. If I ask you to write the Lewis structure for water, you do this. This is non-polar. Does that mean this is linear structure? And if it goes to Lewis, he will say water is non-polar, and this is wrong. Of course, water is a polar molecule, and everybody knows the structure of water. Okay. So in terms of theories of chemistry, we studied about Lewis, okay, and then we talked about VSEPR, and we have now the valence bond theory, which is the VB theory, and we have also something called the molecular orbital theory. MO. Now, MO theory is the best one. It explains everything in chemistry so far. Unfortunately, we're not going to study this because of time limitation. Lewis is the weakest one, and you never depend on Lewis to determine Lewis structures. This is very, very weak model, as you saw here. Even it does not predict the polarity of water. So Lewis is good to start with, but you never depend on it. Okay. VSEPR is okay, but the valence bond theory actually explains better than the valence bond. So as you go down here, these theories, they improve in quality and they give you more results. What is the valence bond theory? The valence bond theory basically is for the VSEPR model based on Lewis structure is used to predict the geometry of a molecule, but does not explain why chemical bonds form. So, okay, we talked about Lewis, we talked about the VSEPR structure, but we didn't say why these bonds are forming, okay, or what exactly the orbitals or what is involved in these bond formation. So, for example, the Lewis theory describes the single bond between H2 and between F2 in the same way as the pairing of two electrons, although their bond enthalpies and bond in a length are very different. Now, two quantum mechanics theories are introduced to provide more explanations on bonding between atoms. So the valence bond theory and the molecular orbital theory, but the MO theory, unfortunately, is not discussed in this course. Now, the valence bond theory assumes that electrons in a molecule occupy atomic orbitals of the individual atoms. Okay, I'm going to explain this in a minute. So, for example, for the hydrogen molecule, the Lewis theory describes the HH bond in terms of the pairing of two electrons on the H atoms. But rather, the valence bond theory is that it describes the covalent HH bond is formed by the overlap of two 1s orbitals. So the difference between Lewis or the VSEPR and the valence bond theory is that Lewis says, okay, a bond is formed between two electrons and that's it. In Lewis structures, we draw electrons and we say, okay, we're going to form a bond between these two electrons. But it does not say if these electrons are sitting in 1s orbital or 1p or 2p or 3d or so on. There is 1p, I'm sorry. And that's what the valence bond theory likes to do. To take as a very simple introduction for the valence bond theory, we're going to talk more about this on Thursday, is that this is the potential energy diagram for H2 molecule. Far to the right here, you have two H molecule, two H atoms that are separate from each other. Okay, so the distance between them is too big. We're talking about few angstroms here, which is at the atomic scale is big. Okay. When these two atoms, of course, a hydrogen atom has one s1 configuration. That means it has one electron only sitting in one s orbital. When these two atoms, they start to attract each other, okay, and come close to each other, the distance between them will reduce. And therefore, you're going to move here from two separate atoms towards a two hydrogen attracting each other. The energy of the system will decrease because these two separate atoms, they are unstable, okay? They want to be with themselves. So the distance decreases and the energy decreases until along this well of energy, until you come up to this point where the two hydrogens are forming a bond from these 1s1, 1s1 orbitals, and this is the best distance where the two hydrogens are sitting. This is called the equilibrium distance for hydrogen molecule. Now, after this distance, if you bring the two hydrogen atoms closer to themselves, there will be so much repulsion between the nuclei, and the energy will rise significantly. As you remember from chapter 6, the higher the energy, the less stability. And you cannot push these two hydrogens so much towards themselves because there will be so much repulsion and energy will go to infinity. And there's a very unstable situation. So there is instability here, but the best situation for these two hydrogens is to form a bond that is sitting at this distance. Okay, the x-axis here is distance. It's not showing up, but the x-axis is distance and the y-axis is energy. This is called a potential energy diagram or potential energy figure for hydrogen for diatomic molecule. So the valence bond theory states that for stable molecule forms from reacting atoms when the potential energy of the system has decreased to a minimum. And this is what whole the valence bond theory is. Okay. Now we understand better why bonds form, because you have a minimum in energy, and in chapter 6 you learn that the lower the energy, the higher is the stability. This is the most stable situation for this molecule. Okay. The Lewis theory ignores energy changes in chemical bond. Lewis and VSEPR does not talk about this. Okay. So H2, it's formed between 1s and 1s orbital. For the valence bond theory, for F2, it's actually 2p orbitals, and for HF, it's going to be from 1s orbital from H with 2p orbitals from the fluorine. And VBT, which is the valence bond theory, can provide explanations for differences in bond enthalpies and bond lengths because the orbitals involved in forming H2, F2, and HF are not the same. So what is the VB theory says here is that you have, like before, let's say you have HF and F2, right? Well, in HF, we only draw a line between H and F, and between F2, it's like that. But what is this line? What is it? It's a bond, right? But what kind of bond is it? Is it the same bond? The valence bond theory says that this bond is between 1s from hydrogen and 2p from fluorine. And here it's between 2p and 2p. That's what the valence theory says. And that's why this bond length and energy is different than this bond, because this bond is between 1s and 2p, and this one is between 2p and 2p. So the valence bond gives you more information, gives you more light, sheds more light on the types of bond, and explain further what is the theory. So that's what about the valence bond theory. And next time, inshallah, we'll do the hybridization and we'll understand things more when it comes to hybridization and why actually bonds forms. So thank you so much for listening to my lecture today. And if you have any questions, I will